Above Earth's restless clouds, far beyond the interference of its atmosphere, a lone spacecraft travels in silence. It is the Kepler Space Telescope, humanity's eye turned outward, built to answer a question older than civilization itself. Are we alone? Kepler's mission is simple but profound: to find other worlds like ours, to search for small, rocky planets that orbit distant suns, planets that might hold oceans, clouds, or even life. After launch, Kepler travels 94 million miles until it reaches a stable orbit around the Sun. There, it fixes its unblinking gaze upon a single patch of sky in the constellations of Cygnus, Lyra, and Draco. Once its protective lid opens, Kepler's instruments stare into eternity. What the telescope sees takes even the scientists by surprise. The night sky, once thought to be sparse, is packed with stars, hundreds of thousands of them. Every sensor on Kepler begins to record light from 150,000 suns at once. Each dot of light holds the possibility of planets, and Kepler's task is to watch them all. Finding planets around distant stars is far more complicated than it sounds. Planets do not shine on their own. They are tiny, cold, and lost in the brilliance of the stars they orbit. Even the most advanced telescopes cannot easily photograph them directly. So astronomers rely on a subtle trick of light, the transit method. If a planet crosses in front of its star, it blocks a small fraction of the star's light. The star momentarily dims, then brightens again as the planet moves away. It's a faint signal, a mere whisper of shadow in a sea of brilliance. But it's enough. The amount of dimming reveals the planet's size, and the time between each dip reveals its orbit. In that rhythm of light and darkness lies the signature of another world. Kepler carries the largest camera ever sent into space, a 95-megapixel array of 42 ultra-sensitive sensors. With these eyes, it begins scanning that single patch of sky, frame after frame, night after night, looking for tiny flickers that might betray the presence of planets. Months pass before the first faint signals appear. The data is unmistakable. Kepler has found worlds orbiting other stars. Each detection sends ripples of excitement through the scientific community. One of those worlds is Kepler 36b, a rocky planet orbiting a star much like our Sun. It's larger than Earth, about 4 times the mass, a so-called super-Earth. For the first time, astronomers are seeing solid terrestrial planets beyond our solar system. They hold their breath, wondering if these worlds might have atmospheres, oceans, or even climates familiar to our own. Kepler does more than just detect planets. It measures them, categorizes them, and reveals what they are made of. With each discovery, it reshapes our understanding of the cosmos. For centuries, we imagined our solar system as something unique, a rare arrangement of planets circling a single star. But Kepler's findings tell another story. Planets are not rare. They are everywhere. Almost every star in the sky is likely to host at least one. The galaxy, it turns out, is overflowing with worlds. While Kepler continues its silent watch, other scientists study the larger structures that make up our home, the Milky Way itself. High above the plane of our galaxy, a vast ribbon of stars stretches across the night sky. It is called the Sagittarius Stream, a looping arc of light that wraps entirely around the Milky Way. This river of stars is not just beautiful, it is evidence of a cosmic collision. The Sagittarius Stream was born when a smaller galaxy, known as the Sagittarius Dwarf, ventured too close to the Milky Way. Gravity tore it apart, pulling its stars into enormous trails that circle our galaxy like comet tails. Astronomers once saw these stars but could not explain how they got there. Now, with data from modern observatories like Gaia, they can track their motion in 3 dimensions and retrace the story of their destruction. Billions of years ago, the Sagittarius dwarf galaxy plunged through the Milky Way's disk. Its gravity punched through the spiral arms, scattering stars and gas, and creating waves of motion that still ripple through the galaxy today. As it passed, the dwarf galaxy lost its own stars, stripped away and pulled into those 2 long, glowing streams we see across the sky. This cosmic collision did more than rearrange stars. It reshaped our home galaxy and may have helped create us. When galaxies collide, they exchange their most valuable substance, gas. Cold hydrogen gas, the raw material from which stars are born. The Milky Way absorbed that gas, replenishing its supply of star-forming fuel just before the birth of our own solar system. Without it, our sun might never have formed. Hydrogen is the lifeblood of the universe. Invisible to human eyes, it can only be detected with radio telescopes. Point a radio dish toward the Milky Way, and you can hear it. Faint signals from the most abundant element in existence. It is everywhere, drifting between the stars, gathering into clouds that collapse to form new suns. Without hydrogen, there would be no stars, no planets, and no life. When astronomers look at these clouds through radio waves, they see the hidden structure of our galaxy. The Milky Way, seen this way, is alive. A vast, rotating system of gas and stars constantly recycling itself. The death of one generation of stars creates the materials for the next. The elements forged inside those dying stars, carbon, oxygen, nitrogen, iron, are scattered into space, where they become the building blocks of new worlds. Our planet, our bodies, and everything we know are made from the remnants of ancient suns. As scientists trace these cycles of birth and destruction, they also look deeper into the galaxy's heart, where gravity reigns supreme. At the very center of the Milky Way lies Sagittarius, a star, a black hole 4 million times the mass of the Sun. Around it, stars race at extraordinary speeds, whipping through space in tight, dangerous orbits. Some come within a few billion miles of the black hole's edge, a hair's breadth in cosmic terms. If these stars have planets, those worlds would face unimaginable forces. The black hole's gravity would stretch and twist them beyond recognition. Their skies would shimmer with distorted light, time itself slowing near the event horizon. If we could stand on one of those doomed planets and look outward, the universe would appear warped and fast-forwarded, the rest of time racing ahead as we were pulled toward oblivion. Scientists call this spaghettification, the process by which gravity stretches matter into long, thin strands as it approaches a black hole. Rocks, mountains, even atoms are torn apart. Beyond that point lies the singularity, a region where matter collapses to infinite density and the known laws of physics break down. It is a place where gravity and quantum mechanics clash, a mystery at the heart of every black hole. To understand how such places form, astronomers look back to the lives of massive stars. When a star 20 or 30 times more massive than the Sun runs out of fuel, its core collapses under its own weight. For a brief moment, it shines brighter than an entire galaxy as it explodes in a supernova. Then, in the aftermath, what remains is crushed by gravity into a tiny, dense point, a black hole. Not every star meets this fate. Smaller stars, like our Sun, will end their lives more quietly. They will shed their outer layers and fade into white dwarfs, cooling embers that slowly dim over billions of years. But for the giants of the cosmos, the end is violent and absolute. Their collapse warps space and time, leaving behind invisible ghosts that still shape the galaxy. Through telescopes and mathematics, scientists can now trace the evolution of the cosmos from its earliest moments to the present day. They see how galaxies grow through collisions, how stars form from gas, and how planets emerge around them. The discoveries of Kepler and the mapping of the Milky Way's streams reveal that the universe is both ancient and alive, a vast system in constant motion. For every new world found, another question arises. How many of them are like us? How many oceans ripple under alien skies? Somewhere among the billions of planets Kepler detected, there may be one where the conditions mirror our own, where sunlight warms an atmosphere, and life looks up at the same stars and wonders the same things. The search for other worlds is more than science. It's a reflection of what we are, explorers driven by curiosity and wonder. From the faint dips in starlight to the violent birth of black holes, every discovery brings us closer to understanding our place in this infinite expanse. As the Kepler telescope drifts silently in orbit, its sensors continue to capture the faint flicker of distant stars. Each flicker is a possibility, each dimming a whisper from another world. And somewhere out there in the endless sea of stars, another civilization may be watching too, searching the skies for signs of us. Far beyond our solar system, the Milky Way stretches like a vast spiral river of light. Within it, stars orbit in quiet harmony, but the history of this galaxy is anything but peaceful. The Milky Way is a survivor of countless collisions, born from the wreckage of smaller galaxies that came before it. One of these collisions still leaves a trace across the sky, the Sagittarius Stream. The Sagittarius Stream is a colossal arc of stars looping around the Milky Way. It's the torn remains of a smaller galaxy, the Sagittarius Dwarf, that was swallowed by our own. For billions of years, the two galaxies danced a dangerous waltz. Each time the dwarf galaxy passed near the Milky Way's core, tidal forces ripped it apart. Its stars stretched into long, glowing trails that wrap around the night sky. These trails are relics of destruction, but also of creation. Modern telescopes, like the European Space Agency's Gaia, can now measure the precise movements of these stars. By tracking their speed and direction, scientists have reconstructed the entire story of the collision. The Sagittarius Dwarf plunged through the Milky Way's disk, scattering stars density where our current understanding of physics collapses. At this singularity, the two greatest theories in science, general relativity and quantum mechanics, no longer agree. Relativity describes the universe on the grandest scales, the motions of stars and galaxies. Quantum mechanics governs the tiny world of atoms and particles. Black holes exist where these two worlds meet and conflict. They are the frontier of our ignorance, the place where space, time, and matter dissolve into mystery. Astronomers have begun to explore this frontier by studying stars that orbit dangerously close to Sagittarius A star. Some of these stars may have planets. If those worlds exist, their skies would be unlike anything we can imagine. The black hole would bend light around it, creating halos and mirror images of the universe. Time would slow near its edge, while the rest of the cosmos raced ahead. For an observer standing there, seconds could pass while millennia unfold beyond. But gravity is merciless. As a planet nears the event horizon, tidal forces stretch it apart. Its near side feels a stronger pull than its far side, elongating it into a thin filament. Eventually, atoms themselves are torn apart in a process scientists call spaghettification. It is the final fate of anything that ventures too close to the abyss. To understand how these cosmic monsters are born, we return to the death of massive stars. When a giant star, perhaps 20 times the mass of our Sun, runs out of hydrogen fuel, its core collapses. The outer layers crash inward and then rebound outward in a titanic explosion, a supernova. For a brief moment, the star outshines entire galaxies. But after the explosion fades, what remains depends on the star's mass. Smaller ones leave behind neutron stars, ultra-dense objects the size of a city. The largest collapse entirely, creating black holes. Not all stars die violently. Most, like our Sun, end their lives quietly. When fusion ceases, the outer layers drift away, forming a glowing shell of gas called a planetary nebula. The core that remains becomes a white dwarf, an Earth-sized ember of carbon and oxygen that slowly cools over billions of years. These faint stars mark the end of a stellar life cycle that began in a cloud of hydrogen. But the story doesn't end there. Even as old stars die, their remains seed the birth of new ones. The gas expelled by dying stars mixes with interstellar hydrogen, creating the next generation. The universe is a continuous cycle of death and rebirth, a chain of creation stretching back to the dawn of time. And yet, even cycles eventually run down. The supply of cold hydrogen in galaxies is finite. Over billions of years, it will be used up. Fewer new stars will form. The existing ones will burn out, leaving behind only remnants, white dwarfs, neutron stars, and black holes. The brilliant age of starlight will fade, giving way once more to darkness. To visualize this cosmic timeline, imagine the universe as a single lifetime. It began 13.8 billion years ago in the Big Bang. The first stars ignited about 400 million years later. Star formation peaked around 4 billion years after the beginning, a time when galaxies were bursting with new light. Our Sun formed much later, about 9 billion years after the Big Bang. Now, nearly 14 billion years into the universe's life, the rate of new star birth is slowing. The night sky we know is already dimmer than it once was. In the far future, even the smallest stars will exhaust their fuel. The universe will grow darker and colder. The age of stars, the age of light, will end. What follows is an era of decay, when galaxies fade into shadows and the cosmos becomes a graveyard of frozen remnants. It will take trillions of years, but that future is inevitable. From our brief human perspective, the stars seem eternal. They guide our journeys, inspire our stories, and light our nights. But on cosmic timescales, they are fleeting. The age of stars is just a blink in the universe's long history, a brilliant moment between two eternities of darkness. And yet, within that fleeting age, something extraordinary has happened. Among the countless stars born from hydrogen and dust, one gave rise to life. On a small planet orbiting an ordinary sun, matter became aware of itself. It began to look outward, to question, to explore. Through telescopes like Kepler, it started to trace its origins back to the galaxies, to the collisions, to the stars that forged its atoms. Humanity became the universe observing itself. Even now, as we map distant worlds and study black holes, we are also glimpsing our own past. The light that reaches us tonight began its journey long before Earth existed. Each photon carries a story, a fragment of the universe's history. Together, they form a portrait of creation, a record of everything that ever was. And so the story continues. Hydrogen becomes stars. Stars create life. Life builds machines that look back and remember where it came from. And in doing so, we close the loop of cosmic memory, turning curiosity into understanding and starlight into meaning. The story of the universe is a story of heat, light, and gravity, forces that shaped everything we see. At the center of it all burns the star that made us possible, the sun. For thousands of years, humans have looked up in wonder, yet only now are we beginning to truly touch it. In the year 2018, NASA launched one of the most daring missions in the history of space exploration, the Parker Solar Probe. Its goal was to fly closer to the Sun than any spacecraft ever had before, to enter its atmosphere and reveal the mysteries of our closest star. The Parker Solar Probe began its journey atop a Delta IV Heavy rocket, one of the most powerful ever built. As the engines ignited and the rocket lifted into the sky, the team below could only watch and hope. The probe's mission was unlike any other. It would orbit the Sun 24 times over 7 years, diving closer with each pass, enduring heat and radiation no machine had ever faced. Eventually, it would come within just a few million miles of the surface, close enough to fly through the Sun's outer atmosphere, the corona. There, temperatures soar to over 1,000,000 degrees, and yet the spacecraft would survive, protected by a carbon composite shield no thicker than a few inches. The Parker Solar Probe was designed to answer questions that had baffled scientists for generations. Why is the Sun's atmosphere hotter than its surface? How does it eject charged particles that fill the solar system and shape the space weather around Earth? The answers lie in the chaotic magnetic fields that twist and snap across the solar corona, sending waves of energy outward. By touching the Sun, the probe would not only reveal the secrets of our own star, but also help us understand every star in the universe, including those that gave birth to the Sun itself. As the probe completed its early passes, it sent back streams of data unlike anything seen before. Images of solar storms and waves of plasma curling through space. Each bit of information brought us closer to understanding the engine that powers life on Earth. For the first time, humanity was reaching out to the very source of its own existence. While Parker studied the Sun's present, Other missions looked back toward the universe's past. The Hubble Space Telescope had already shown us that the universe is expanding and that the expansion is accelerating. That discovery implied something extraordinary, that if you could reverse time, everything would contract back to a single point, an unimaginably dense and hot state. The universe, it seemed, had a beginning. That beginning is what we call the Big Bang. Not an explosion in space, but an expansion of space itself. 13.8 billion years ago, all matter, energy, and even time were compressed into a tiny region smaller than an atom. In an instant, it began to expand, cooling as it grew. In those first moments, the universe was a soup of fundamental particles, protons, electrons, and photons colliding in chaos. As it expanded and cooled, those particles combined to form hydrogen and helium, the first elements. From that simple mixture, everything else eventually emerged. To study those first moments, astronomers needed to look deeper than visible light. They needed to find the faint afterglow left behind by the Big Bang itself, a background of microwave radiation that fills all of space. In 2009, the European Space Agency launched the Planck satellite to measure this ancient light with unprecedented precision. Unlike telescopes that study stars, Planck was designed to study the universe itself. It scanned the sky in microwaves, mapping temperature variations just a few millionths of a degree apart. What Planck found was a snapshot of the universe as it was just 380,000 years after the Big Bang, the moment when light first broke free and began its journey through space. The image it captured showed a pattern of faint ripples, tiny fluctuations in density that would one day grow into galaxies, stars, and planets. Those ripples were the fingerprints of creation. With Planck's data, scientists could measure the exact age, composition, and shape of the universe. They discovered that only about 5% of the cosmos is made of ordinary matter, the atoms that make up stars, planets, and people. The rest is invisible. 27% is dark matter, a mysterious substance that holds galaxies together through gravity. The remaining 68% is dark energy, a force driving the universe's accelerating expansion. Together, these findings revealed a truth more astonishing than anyone had imagined. Most of the universe is beyond our direct perception. Even so, the patterns from the Planck mission confirm that the Big Bang theory is correct. The universe truly had a beginning, a moment when space and time themselves came into existence. Every galaxy, every atom, every living thing can trace its origin back to that instant. From the Big Bang came hydrogen. From hydrogen came stars. From stars came elements. From those elements came planets and, eventually, life. into the atoms, the stardust, the ancient light that made us. The universe is vast beyond imagination, but it is not separate from us. We are part of it. We are its witnesses, its storytellers, and its fleeting consciousness. As long as we keep searching, the universe will never be silent. Its wonders will continue to unfold. In the light of distant galaxies, in the pulse of dying stars, in the faint echoes of the Big Bang. We may be small, but we carry within us the memory of everything that ever was. And so, even as the stars fade and the night deepens, the light that began at the dawn of time continues to travel. It crosses the void, reaches new worlds, and perhaps, somewhere far away, touches the eyes of another being wondering who they are and where they came from. The universe began in darkness, burst into light, and through us, it has found a way to look back upon itself. That light still travels, the same light that was born 13.8 billion years ago, the same light that forged the stars, illuminated the planets, and sparked life on Earth. It will continue long after we are gone, carrying the story of everything that ever lived. In that story lies the truth of who we are. Fragments of the universe, bound by gravity, fueled by starlight, and destined to one day return to the silence from which we came.